So this is part 1 of the series on MOS transistor short channel effects. By the end of this video, you'll be able to understand the physics behind channel length modulation and how it actually impacts the circuit design. To get started, we have to understand how the inversion charge actually builds up in the channel region of the MOS transistor, specifically during strong inversion, and what happens to this channel charge when we actually apply drain source voltage across it. So before we get started into MOS transistors, let's look at a simple parallel plate capacitor. Suppose both the plates are made of metals and the capacitance of this capacitor is Cox, and when we apply a voltage Vg and Vx across it, the charge stored in this capacitor is given by Cox Vg minus Vx. Now let's say we replace one of the plates with a semiconductor. Let's say we replace the bottom plate with a p-type semiconductor. So what I mean is, the top plate is a metal and the bottom plate is a p-type semiconductor. Suppose the capacitance is Cox. Now we have to find what is the charge stored in this capacitor. So in this case, we have two conditions. One is Vgx less than 0 and one more is Vgx greater than 0. The first condition is actually called as the accumulation mode, and the second condition is called as depletion and inversion. So in this video, we'll be looking at this second condition. So that is, when Vgx is greater than 0, what is the charge stored in this capacitor? So it turns out that the charge stored in this capacitor is given by Cox Vg minus Vx minus Vth. So you have this additional term, that is Vth, which is the threshold voltage of this capacitor. So what this means in simple terms is that the charge does not appear immediately at this bottom plate as it did in case of a metal capacitor, and this is because the semiconductor needs to be first depleted and then inverted for the charges to start appearing at this bottom plate. And the amount of voltage required for the semiconductor to go through this process is the threshold voltage, which is given by Vth. So when the voltage applied across this capacitor goes beyond Vth, then whatever excess voltage we have applied actually gets stored as charge in this capacitor. So now let's get back to MOS transistors. So we will look at a cross section of a simple NMOS transistor and we'll see how this actually relates to this capacitor. So in the MOS transistor, we have the source terminal, the gate terminal and the drain terminal. And for now, we will actually ignore the substrate terminal. And if you actually compare this with the capacitor that we had, the gate terminal is the top plate of the capacitor and the bottom plate is this channel region. So this is where the voltage Vx was applied. So when we actually apply a drain source voltage across this MOS transistor, it turns out that the Vx is not constant anymore. So what I mean is, let's say I ground the source and I apply a voltage source at the drain terminal. So in this condition, the voltage Vx, that is the voltage of the bottom plate of the capacitor, is no more a constant as it was before. So we have to actually understand how this Vx changes as we move from source to drain region. In order to do that, a simple way is to picture the channel region as a chain of resistors from source to drain. So what I mean is, just to note, this is the channel region I'm talking about. So what I meant was, we have this source and we have this chain of resistors. Let's assume the resistors are equal, that is going from source to drain. And when we apply voltage Vds across the MOS transistor, that is, I ground the source, and when I apply a voltage, let's take an example. Let's say we apply a 2 volt voltage source at the drain terminal. We see that the voltage at these intermediate nodes actually increases as you move from source to drain. That is, at this point it is 0.4, 0.8, 1.2, 1.6 and eventually it goes to 2 volt. So we can see that this intermediate voltages is nothing but Vx, and this Vx increases as we move from source to drain terminal. So looking back at the expression for the charge stored in this capacitor, the charge was given by Q is equal to Cox Vg minus Vx minus Vth. So we can see that Vx is actually subtracted from this expression. So it clearly tells that the charge actually reduces as you move from source to drain. And one thing we can note, that is, the charge can indeed go to 0. That is, at this condition, when Vg minus Vth is equal to Vx, the charge stored actually goes to 0, And this condition is actually referred to as the pinch-off condition. So if we actually take a look at the cross section again and see how the charge is getting distributed, we see something like this. And at this point, the charge is actually becoming equal to 0. So we can see that as we actually increase this drain source voltage, this Vx actually increases. And once this Vx increases, and the point at which the total charge becomes 0 starts moving towards the left. But one thing to note that is the rate at which this point moves towards left is not exactly proportional to the rate at which we actually increase the drain source voltage. The reason is this region, there is no charges. So this is the depletion region. So actually this can be derived using simple electrostatics. But what it simply means is that, so when you start increasing the drain source voltage, the voltage drop across this region goes linearly with X. That is, as you start moving towards the right from source to drain, the voltage drop increases linearly, as we saw before, by assuming that the channel region has a simple chain of resistors. We saw that the Vx was actually increasing linearly from source to drain. In this depletion region, it turns out that the voltage drop goes by X square. So what this means is, even if you start increasing your drain source voltage rapidly, the maximum amount of voltage drop now appears across this depletion region rather than this channel region. So this is what actually happens in reality. But still there is some voltage drop across the channel region that is getting increased due to the fact that you're increasing the drain source voltage, because of which this point at which the charge becomes 0 starts moving towards the left. And this is called as channel length modulation. Basically, the length of the channel is getting modulated by the drain source voltage that we are applying. So what I mean is, initially the length of the channel was L, and because of applying the drain source voltage and this pinch-off condition, now the length got reduced by a factor L prime. So now the effective length is given by L minus L prime. So we can actually take example and see how the L effective is changing. If your channel length was 1 micrometer, your L prime would be around, let's say, 20 nanometer. Then L effective was 980 nanometer. So if your channel length was small, let's say if it was 100 nanometer, then L prime was 20 nanometer, then the effective channel length is now only 80 nanometer. So we can clearly see that in the first case, the reduction was only 2%, but in the second case, the reduction has now become 20%. So what this means is, as you start shrinking your channel lengths, the effect of this channel length modulation becomes significant in short channel devices. So this is regarding the physics of channel length modulation. Now let's look at the impact it has on circuit design. So in order to do that, we have to first understand the IV characteristics of MOS transistor. Basically, how channel length modulation affects the IV characteristics of MOS transistors. Particularly, we are interested in the output characteristics, that is the ID versus VDS curve. So in ideal MOS transistor, this is what we expect. So what we see here is, this region is the linear region and this region is the saturation region. That is the voltage beyond the pinch-off region. So this is the point where pinch-off happens. So beyond that, if you increase the voltage, we see that the current ideally should have been constant. But what happens is, because of this channel length modulation, we'll see that the current is not constant in this saturation region. The current actually increases as you increase your drain source voltage. And this is due to channel length modulation. So if you actually look at the slope, ideally the slope should have been 0. But now what has happened? The slope is some positive number. And the slope is nothing but dou ID by dou VDS, which is equal to the inverse of the output resistance of the MOS transistor. So now the question is, what is the impact of this output resistance on the overall performance of the MOS transistor? So to understand this, let's look at an ideal current source. So suppose I have a current source of 10 milliamps. Now I go and connect a load across this current source, RL. So now if we see what is the current flowing through this load, it is 10 milliamps. Now, irrespective of whatever load you have, the current actually remains constant. But in the non-ideal case, what has happened is, you have a finite output resistance across this current source. That means it has a finite output resistance. So now if we go and connect a load across this current source, we can see that the current delivered to this load is now dependent on the load that you tie across this. So basically the current in this branch is given by 10 milliamps into R0 by RL plus R0. So now it actually depends on the value of RL that we choose. So this is what actually happens because of channel length modulation. Ideally, the output resistance should have been infinite. That is, the slope should have been 0. But because of channel length modulation, we have a positive slope, which results in this finite output resistance, because of which the current now delivered to the load depends on the load that is actually tied to this current source. Now let's look at two simple circuits and understand the impact channel length modulation has on the performance of these circuits. So the first circuit we'll be looking at is a simple current mirror. So a simple current mirror looks like this. And I make sure that both the transistors are in saturation and their dimensions are same. That is, both of them have the same W by L ratios. And now we can see that both the transistors have the same VGS. So in ideal condition, we saw that when the MOS transistor is in saturation, the current is actually constant. So since these two transistors have same VGS, if the current in this branch is I0, then the current in the second branch should also be equal to I0. But it turns out that this is not exactly true, because the current now not only depends on VGS, but it also depends upon this drain source voltage that these both transistors see. If this VDS1 is not equal to VDS2, then we see that there is a mismatch in the current that is copied in the second branch. That is, I1 is not equal to I2. Okay, so this is one place where channel length modulation actually affects the circuit performance. And one more case is we can take a simple common source amplifier. So if we actually look at what is the small signal gain of this amplifier, the gain is given by minus GM RL. So this is the ideal condition. That is, we are assuming that the transistor does not have channel length modulation. What it means is the resistance looking into this drain terminal is infinite. That is, the slope was 0 in ideal condition. But we saw that because of channel length modulation, that is not true. That is, it has a finite slope, and the resistance looking into this drain terminal is not infinite. It is a finite resistance that is given by R0. And because of that, what happens is the gain actually reduces to GM times RL parallel R0. So note that I'm talking about small signal gain, and this R0 actually comes in parallel with this load resistance. So in theory, even if you try to make RL very high to get high gain, but R0 actually limits the overall gain of the amplifier. And the reason for that is the R0 is actually coming in parallel with RL. So if you actually have two resistors in parallel, then the effective resistance actually turns out to be lesser than the least resistance in that parallel branch. So basically, this combination always leads to a resistance that is less than R0, and therefore the gain is actually reduced. So in this way, we can see that how channel length modulation affects a simple common source amplifier. So this is regarding the impact of channel length modulation on circuit design. So that's the end of this video. That is part 1 of the series on MOS transistor short channel effects. So thanks for watching and see you in the next one.